Hubbard-Platonovich transformation and look what is the spin fluctuational contribution into free energy, basically we immediately see that spin fluctuations select one of the diagonals in xy plane, and it helps to satisfy this second neighbor Kitaev interaction, isotropic Kitaev interaction. So basically here we didn't have any other fitting parameters. And if we vary our parameters but still stay in this zigzag phase, the direction will be still 45 degrees, quite robust. Okay, so I didn't answer only to one question, why it's ordered, and I will show you why it will order, why it is not spin liquid anymore. But in any case, our suggestion was, okay, so since Kitaev interaction of the second neighbor is important, why don't we look to the minimal model and get rid of all Heisenberg interaction and basically consider only Kitaev interaction by analogy of J1, J2 model, which was studied by many people and apparently holds many interesting phases. So we were trying to see what is interesting about this K1, K2 model. And once again, what is important in our microscopic calculation, we got it in a very symmetric way. So basically adding K2 terms does not lower the symmetry, because if we have two iridium sites which from nearest neighbor connected by green and red bonds, so let's say by X and Y bonds, then the second neighbor interaction will necessarily be this type of interaction. That's why this model contains the same kind of symmetry. Okay, so we start by analysis of classical K1, K2 model. And there's the usual way how one can do it is using the Lassiger-Tisa theorem. So basically here is, so we go to Fourier transform and we diagonalizing these lambda matrices. And what is important here, because it's not a Heisenberg interaction, now we have three types of eigenmodes corresponding to X type of spins, X directional spins, Y directional spins, and Z directional spins. And basically we have to look to the minimum of these eigenmodes. And one can immediately see that the minimum lines on the minimum sits on the lines in the K space. And basically what lines, these lines or that line, depend on the sign of K2 interaction, because it depends on this K2. So basically K2 interaction, which actually couples the triangle lattice, I will talk about triangle points separately, determine the type of classical degeneracy of the model. So degeneracy of the ground state is free because it can be three different lines, and 2 to the power L, where L is the number of ladders, because the ladders are formed by non-zero K1 interaction. And basically this degeneracy, classical degeneracy, is not accidental because it's related to the symmetry of the Hamiltonian, and the symmetry is sliding symmetry. In a moment I will just explain what is this symmetry, and it's kind of gauge-like symmetry, and therefore for classical spin at t equals 0, this cannot be broken. Okay. So basically, let me construct, looking to this degenerate, let me construct one of the states. Let me satisfy all the Z bonds. Basically, I will be looking to the minimum of lambda Z eigenmodes. So in this plot, so my Z bond, nearest neighbor Z bond, is my vertical bond, and my next nearest neighbor Z bond is my horizontal bond. So I consider both coupling ferromagnetic, K1 and K2, and basically I'm satisfying all these bonds. So I satisfy all the bonds on the nearest neighbor, and I satisfy all the bonds for the second neighbor. But because spins are classical, so the interaction, the coupling between these ladders by X and Y bonds, and basically for classical spins this gives no coupling. And therefore I have a symmetry. Basically I can take any of these ladders and I can flip it, and the energy of the Hamiltonian will be the same. So I can flip all the yellow ladders and get the ferromagnetic state, which will also be the classical ground state. Or I can take just one yellow ladder, flip it, and will be also ground state. So basically, all the points laying on these QZ vectors, these horizontal vectors, will correspond to the classical ground state. So the classical order is nematic-like, but at t equals 0, it's all the states with ladders in z direction, x direction, and y direction. They're all degenerate among each other, and basically in the space of the classical ground state, they are also connected. This is just another example where I took all signs of interaction antiferromagnetic, but the story is the same. So my ladders are now antiferromagnetic, and basically I can flip one of the ladders or all of them. So classical state we studied by classical Monte Carlo. So at high temperature, what we see all this. So this is the structure factor obtained from classical Monte Carlo, and we see that at high temperature, all these lines are present. And basically, what happens is below certain temperature, which we call nematic temperature, only one direction is chosen. So it's spontaneously chosen only one Z ladders, X ladders, or Y ladders, and basically you have nematic state. Of course, classically, you have, it's not a Kitaev syndicate because it's a quantum state, but it's classically degenerate state, so you don't have even nematic order in the vicinity of Kitaev point. So basically here, this direction corresponds to K1 interaction, and this one vertical direction corresponds to K2 interaction, cosine and sine. Okay, so then we look to the quantum K1, K2 model, and here the long-range magnetic order is actually possible due to quantum nature of the state, and actually describing symmetry is simply absent in the for quantum spins. The simplest way one can see it is looking to the state, looking to this coupling perturbatively, and one can see that these ladders, they are not coupled to the nearest neighbor, but they are coupled to the second ladder. And I will talk about this because it was similar calculation done by triangular lattice by George and by Adolfo Abela. I will comment on this later. So basically, in our case, we have three types of processes. It's the processes which involve only K2 interaction, the processes which involve K1 and K2 interaction, this green one, and probably you don't see, but these processes which involve only K1 interaction, and these interactions, like the same interaction are present in the original toric-like interaction in the Kitaev model. So, so basically what we did, we did a perturbation expansion. We first assumed that X and Y interactions are smaller than Z interactions, and we start from the state where basically all Z bonds are satisfied and see how this long-range magnetic order can happen. So X is smaller than 1. And once again, this is this three different processes. So the processes coming from this type is J1 effective coupling, and this is 2 effective coupling. This is the third effective coupling. Basically, and as I said, the same kind of coupling was obtained by George and by Adolfo for triangle lattice. What is important that this coupling actually choose the order according to the sign of K2 interaction, and it can be both ferromagnetic and antiferromagnetic, while the coupling which involve the mixed K1 and K2 interaction, you have to take all these terms into account, appears to be antiferromagnetic. This term effective coupling free, actually supports spin liquid. Historic term supports spin liquid. And that kind of term is present in the original paper by Alexei Kitai. So, what are the competing phases? In fact, one can show that this coupling number, J effective 1 and J effective 2, these first two coupling, they compete to each other. Because this coupling which involves only K2 interaction, if both K1 and K2 is antiferromagnetic, then it wants this spin and that spin to be antiferromagnetically coupled. But in this case, in order to satisfy all these interactions, basically this term, so if effective coupling 1 is dominating, then this ladder coupled to that ladder are antiferromagnetic. If we consider that the second type of coupling is larger than the first one, then it's preferred to couple the third neighbor in antiferromagnetic manner, and